10 o'clock. So give you all time to get in and get answers in. You can take to like 10:03, 10:04. After maybe some stragglers, give them the opportunity. What's on Blackboard? And we're at 5:9. A reminder for everyone, this is going to be the same thing throughout the entire semester. That link doesn't change, that name doesn't change, so make sure you do whatever you need to do to make it easy for you to access. We got one more minute to get answers. First question? This is the only question. Always going to be just a single question in class. It will always be related to what was covered the last. So since this was in the last video that you watched, I made it today's video this. I'll give y'all 30 more seconds. Well, we have 7 responses in. That we have 1 0. Make sure you use your actual name, not bottom fragger. If I don't know who that is, that means you're not getting it right. I'll give you all 10 seconds. I'm going to lock answers here. 5, 4, 3, 2, and 1. All right, so that is pretty much how every class is going to start. By any of my classes, you'll see it, whether it be say college trade or my abstract algebra course. Always start with these daily quizzes, because I want you to make sure that you're looking at your notes beforehand. And it can be a quick skim, I don't care, but you're at least looking at them and you're thinking when you come to class. Okay. Who remembers how I grade daily quizzes? Yeah, something like that. You're close. So it's always out of 3 points. Okay. 3 out of 3 means you got it correct and you're here. Caveat, people like to think they can just take this and not show up to class. That's not going to fly. All right. 3 out of 3 if you're here and get it correct. How do you get a 2 out of 3?
If you get it wrong.
Yeah, if you're here and get it wrong. Okay. How do you get a 1 out of 3? If you show up, you either don't answer it, or let's say you show up late, right? Still gonna at least get you a 1 out of 3. Only way you can get a 0 on any daily quiz is if you don't show up at all. Okay. So that's a reminder just kind of on that. So when you start seeing these daily quizzes pop up in Blackboard, you can see a 3 out of 3, means you got it correct. 2 out of 3, incorrect, but you're here. 1 out of 3, I saw you here, but I didn't get an answer from you. 0 out of 3, you didn't show up. Okay. Well, other thing I'm always going to do is go over the daily quiz. So we'll get seen in. Oh, that will help you right now. Where are we? One of the reasons why I like to use Pull Everywhere. Well, no, it's not shown as well on this screen. Is you can at least get to see, and I can show you some anonymous answers to see what people said. But I want to ask you this question: which was the right answer? When is the only time that implication P implies Q is false? I have mumbles. It's going to be whenever P is true, P is false. We can think of it a little logically, right? Why is that the only case? Well, we start with any implication your hypothesis, right? It's that first part before the error. You want to satisfy this. If you satisfy this, then we can move on to the second part of your statement. For you programmers, that's what you do anytime in if then statement, right? The only time that's going to be false is if I let you go on to the conclusion and I lie to you about the conclusion. Right? I give you a falsehood. Otherwise, if you never get past the hypothesis, right, the beginning part, the if part, then does it really matter what the conclusion is? No, never matters, right? So the implications are always true because you never actually pass the first barrier of entry, never pass the hypothesis. So, correct answer is 50% of you answered correctly. E is true, Q is false. All right, now, before I start lecturing, what questions do y'all got? I know we didn't really have a normal first week or a syllabus day like some people like to have, because I was gone in the conference. So what questions do I got? Go ahead.
What's the best way to memorize maybe truth tables and how to tell which is true or false for each sort of conditional or any of the
So the best thing to do is remember your 4 basic points and or if then and by condition. If you remember those 4 statements, then any thing that you piece together of those, you'll be able to figure out, or at least use. So always start with those as your building blocks. How to memorize those, that kind of depends on your brain. The easiest way, and part of the reason why we always encourage taking notes is write it out. There is a known link that if you write things out, better change memories. Right? If you just watch those videos or just watch them without writing anything down, most of you will probably remember 20%. what actually was being talked about in those videos, but the fact that most of you, I think actually in this class, everyone gave you notes. Some were iffy, but everyone did give you notes. I bet you now have a way to at least remember all the stuff that's in those videos. So when we get to what we're gonna do today, it's gonna be really easy, right? So still take that into consideration for not only this course, but all the other courses. Actually write stuff down. It might be hard, it might be difficult trying to keep up, but I promise you it'll help you out when you come study the test for you. All right, what other questions you got? Share screen. There's- Look at new technology. I'm enjoying it. Very much so. But still haven't used it. Okay, so let's start just filling out the truth tables here. I do it slightly differently than what was presented in videos. Videos is something that's a little bit more familiar for computer scientists, because what you usually represent numerically is true, 1, and false, 0, or on off, right? True, false, on off, whatever you want to say, it's fine. Right? They're all just symbols to represent the same concept. So let's start with some simple ones. That little V. So that would be, what does that represent? Right? The one or statement's true.
The highest truth value for the two.
So you can think of it like that. But we can simplify a little bit more, and you're close. But what you gave me was, the exclusive. Exclusive one. Or a statement that's going to be good whenever at least one part of that statement is good. Right? I'm either hot or it's very sunny outside. As long as one of those two parts of that statement is true, then that entire or statement is true. So go along the first line. I don't care what these molecular statements are, but as long as they're both true, then the or statement, P or Q, is then going to be what? True. All right, if P is true and Q is false, then P or Q is going to be still true, right? Because at least one of those two is true. Third one, P is false, Q is true. True. And the last one, both are false, so the or statement is false. Neither of them were true. Right. This is again, like we were kind of discussing, one of the basic tenets of logical symbolism, I guess. Let's stick with that. But as long as you remember that, true in all cases except for one, and both parts are false. What about that second one? Other symbol. You do it. Oh, other thing, a couple of y'all have had class with me before. I usually look for a cacophony of answers and I'll pick the right one out. I like that because even if you're wrong, usually you'll just kind of get drowned out. So you don't have to worry about getting wrong, and also I don't care if you're wrong. I just want participation. Right? I even get bored if it's just me up here talking for 50 minutes. Okay. So don't worry about raising the hand or any of those formal formalities. The other one is an and statement. And statements are true only when what? Yeah, both parts are true, right? They both have to be true for and statement, which means when I'm going down this column, I can already predict, oh yeah, got a little cheat sheet here in Zoom. Right, it's only going to be that first instance when both P and Q are true. That's the only time that composition, that and statement will then produce a true compounded statement. All right, and or the two basic ones that we always deal with. What's another statement? It's another molecular statement. So we combine two atomic statements, like a different way to do P and Q. Yeah, if then. Yeah. All right, if then's one of them. How do we represent symbolically an if then? There. Okay. This little arrow. Oops. If then statements are probably one of the most important that you deal with in mathematics, even in computer science, when you're thinking about programming, different structures, any other type of thing that you're doing, while loops or for loops are all just if then. Just are if then structured in a different way. But kind of like what we discussed, the only time this implication is going to be false is when what? First one's true and second one's false. So of the rows, which is that condition, first, second, third, or fourth. Right? Second. Otherwise, the implication is always going to be true, even when we're going to feel a little icky in these last two cases, right? But it's because when I'm saying P implies Q, if P is false, then do I ever pass that? Do I ever pass the hypothesis? Do I ever pass that first kind of checkpoint? No. Then anything afterwards doesn't matter. It can be anything. It's something ridiculous, right? So let's just stick with that. What's another one? Another way to combine these atomic statements with P and Q. So only if is a different way to say if then, but I think it got corrected too. And if only if. Which, what do we call that? Starts with a B. By condition. By condition. So by condition is a little bit stronger than implication. How do we get the truth values for this? Yeah, they have the same truth value. So both parts of the statement, P and Q, have to be true, which means if I go along these rows, that first row, I look at the biconditional P if and only if Q, is that going to be true or false? True. First one's going to be true. What about the second? False. Yeah, false, because one of those two statements is false, the other one's true. Next one. False. Last one. True. Because both of them have the same value, they're both false. P is false if and only if Q is. Now, there's one more, so I get caught up. There's one more thing we can do to those atomic statements with P and Q. Saw it a couple times and they saw it a lot in the videos. I have an idea of what it is. What do you mean by inverse? Like not. The not statement. Yeah. So just flipping the value of that atomic statement, that's the P or okay. So I'm gonna, so I can keep it all the same. Our textbook uses this symbol right here, kind of like a sideways L. That's not the way I learned it, so I'm going to stick with the textbook. It's going to be my thing I'm going to try to do. If you do see a little tilde or a squiggly, That's another way to denote the same concept. Just doing it again. So if I added this to my nice little table of columns, which one do you want to negate, P or Q? Or P first? So if P is true, then not P is false. So the first two rows become false, false. And then if P is false, then not P becomes true. Right? Now, whenever we start nesting some of these together and you kind of see it in your homework, you still break it down to these kind of 5 basic tenets, right? Even if I have more complicated things on either side of that or statement, I'm still looking for, is everything before the or statement true or everything after the or statement true? Okay. And that's going to then determine if that full-on statement is true or false. So try to do one real quick. If you are, let's look at like this. Let's just go through all the different scenarios. There's going to be a lot of them. There are 3 different molecular statements here. Or atomic statements. I'm going to get my language correct. I'm going to blame Jeff. Wait, at least for the next couple of minutes, right? After that, we have a situation where all are true. What else? And true, false. Let's do all the cases where one is false, right? False, true. True. What else? Yeah, we'll say the all false at the bottom. Let's go. True, false, false. True, false. Yeah. And then that last one. All of them are false. Now we're not going to go through every single one of these ones so you can complete it on your own. Let's just go through a couple rows. All right, we kind of figure out what's going to happen. And just like how you would want to do if you're move that mouse out of the way. If you're, let's say, doing algebra homework, right? You don't necessarily want to just try to jump to the end step or try to do a bunch of arithmetic in your head. Same thing can happen here. Right? You can break down that bigger molecular statement to smaller molecular statements. So, for example, what are the 2 different conjunctions that we have going on? Yes, we have which one is this one? Or statement here, and statement here. And we use still kind of PEMDAS a little bit, order of operations. Which of those statements will I want to evaluate first? Q and R, right? Figure out when those are true, and then from there, see, okay, well, whenever this part is true, look at it, or false, look at it with P. And then declare what that or statement is going to be, true or false at the end. So let's just break it up. Let's first figure out what are the truth values for Q and R. Because then I'll know what the truth values are for that second part of that or statement, always. And I just have to compare it to P to figure out whether or not that or statement is true or false. All right. Well, first instance, first row. If Q is true, R is true, so Q and R is true. Let's mark it on some rows. Actually, we should probably get through quickly. Second one, false. It'll be false, but one of them is or the opposite. Next row, I have Q is false, R is true, that'll be false. And both are true again, that'll be true. False and false. That's false and true. There's some other ones I want to make sure. Okay. Everything else. Lining up correctly, false, false. 1, 2, 3, 4, 5, 6, 7, 8, 9. Lining a little weird, but it should be 9 total. 3, 4. Yep, okay. All right, well, now that I understand, and one mark. Now that I understand what the truth values are of that one statement Q and R, and then I can go figure out, okay, well, what happens when I pair together E or that statement Q and R? Now I just look at both those two values. So first row, E is true, Q and R is true, which means the or statement is true. To what color? Green, blue, or red? Heard green first. I did hear everything, but I heard green first. All right, next row. E is true, Q and R is false. Is that going to be true or false? Because at least one of those two for the or statement was true. Next one, true or false? Again, fourth one. Let's see, we've got. Yeah, so fourth one should be highlighted. Yeah, so fourth one, you're gonna have false and true. I'm gonna do this, and I'll go to the next view. I don't know why you're doing this out. It breaks down. Right now. Then what am I missing? No. And we'll figure it out as long as we have 9 at the end, right? The next one, the fourth one, we have P is false, Q and R is true. So that overall statement is going to be. All right, next one, the oranges, I know those are matched correctly. Yeah, so we have a true and a false, but for the or statement, one of them is true, so the or statement is true. Next one. Yeah, that one's going to be false. Because both P is false and Q and R. And then what about the last one? So if they're false. 2, 3, 4, 5, 6, 7, 8. I'm missing one. I'm missing. So I'm missing one combination. Anyone determine what the combination is I'm missing of P, Q, and R? There should be 9. Now we're doing permutations. 3, 2 times 2 times 2, so it would be 8, yeah. Yeah, it would be. So I did have one too many. I promise I did look up, they usually have lines on me, make it a lot easier for all of us. Spend about 5 minutes doing Google searches to no success, because it's like a free version. Probably bells and whistles. But the main thing is learning how to combine those molecular statements. Even if you make a long, nice long list, it all comes back down to breaking apart logically those 5 that we were dealing with before. Now I can scroll up. I love technology and look at it. There we go. It all just comes back down to those 5. What questions do I got?
What if you could explain the mythology?
Pathology? The end of the video? I have to see it in context, but I don't recommend to talk that word. Is that where you're talking about the comparison of like implication and contra-positives are the same?
Mythology is when the 4 statements are true. But this is the same thing as being said twice in one statement. One explanation I got for it.
So which video was it in?
One of the later ones.
One of the later ones, not the last one. So
Yeah,
for-
like two, like two in both columns
Mhm.
and,
culture, so it doesn't matter. What might be one of you computer scientists, the ones that have vision over that use,
well, that important.
not in this class, I'll say, good question. At least that'll be my top out answer for now, but I'll go back and look at them, you've got to teach at 11, right, after that class, I'll go back and rewatch it, pick that up, and we can be better answer on it. All right, any other questions? Yep. Everyone did. There's a couple of ifs with the note taking, but I'm gonna be gracious. Since you, at least everyone seemed to actually put in the effort. Okay. All right, any other questions? So one of the cornerstones that we're gonna be having in this, over this entire course, we'll dip into it a couple times, we'll get away from it, we'll come back to it randomly. So it's gonna feel like something called proofwriting. Okay. Proofwriting is all around those implications. Okay, so we want to prove an implication to be true, and this isn't saying like, okay, are we going to the logical sense of is implication true of or looking at molecular statement broken into the atomic parts, right? Whether or not P is true, Q is false, you can always write down the table real quick. Q, true, false, false, true, false, false. And P implies Q, what is that going to be? False, true, true. Okay. So when we start investigating these, there's really only 3 implications we're going to care about, right? Technically, it's the ones that are true. We don't want to deal with anything that's false. But even when I look at all those 3, how many of them will I actually really care about in the real world? Just one, the true truth. And the hypothesis is true, and the implication is true. Right? That's what I care about. That's what I'm going to be seeing in the real world. If this happens, then I can guarantee this happens. Right? Technically, I can make true implications where the beginning is false. If the sky is an azure purple, I don't know, right? Then there will be an economic collapse in 2059, right? I can make ridiculous statements, whereas as long as that first part of that hypothesis is true, you're never going to be able to debate me on the second part because we're past that gate, that entry. So when it comes to proving things in mathematics, yeah, there's technically 3 ways an implication is true, but what's the only one we really care about? True. That's the one that's always the most important. In proofs, the idea behind proofs is very, very simple. You're given a hypothesis, and you want to show that given that hypothesis being true, the conclusion also has to be true. Now you get to use different tools, mathematical tools with all of that. And the tools, the most basic mathematical tools that we start off with are what are called definitions. So we're always going to make sure we're clear in defining the tools that we're going to work with. We don't want to leave any room for ambiguity. Right? And when you kind of first start out with the mathematics courses at this level, we're going to be defining very basic things. Like, for example, what does it mean to be an even number? So first definition, integer x is said to be even so what we're defining is what does it mean to be even here? If there's this an integer n such that that integer x can be written as 2 times the range. And that's how we know even numbers do, right? 6 is an even number because how can you rewrite 6? 2 times 3, the multiple of 2. 8 is an even number because 8 is 2 times what? 4. Right? That's how you've always known even numbers to be, but we can write it out explicitly, right? Now, is there any confusion on what we're going to be defining even number? No. Well, not only can we define even numbers, but we can also make a definition for an odd number. We're going to leave it blank for a second. One, let you get caught up, but two, but you can also fill in this definition. An integer x is said to be odd, so we're defining what it means to be odd here. If there exists an integer n, such that x is equal to 1. I'm going to default to 2n plus 1, because I'd rather not use minus, but minus 1 is more than adequate. Since we're dealing with integers, that's fine if you're dealing with natural numbers. That's what it means. But these also are now going to give me tools so that I can do a proof, something called a direct proof. And direct proofs are necessary for something called theorem. So I can take these tools and say, I can create something with these concepts. So for example, one theorem that we can make is that if A and B are even integers, if I add them together, their sum will also be an even integer. We probably know this innately, run into it a lot, right? 2 plus 2 is 4. And if 2 even integers added together, and even. 28 plus 16. What's that going to be? Yeah, 47, 46, I think. But anyway, more don't care about what the end result is. Is it an even number still? Yeah. 44. All right. Y'all correct. I didn't want to actually do the arithmetic. That depends on y'all for that. That's the reason I got my PhD. I don't want to do that stuff. No, I'm kidding. All right. But those are just examples, right? I can give you examples, but how many, just from your experience, how many integers are there? A lot. How many even integers are there? Infinitely. We'll see why eventually. There's an infinite number of even integers, right? I can keep counting that rhythm. 2, 4, 6, 8, 10, 12, 14, 16. I can technically let that go on and on and on until time stops and then technically you can keep going. Okay? So I can't prove this statement. I can't guarantee you this statement's going to be true by listing every example because there's infinitely many of them. So I have to think of a new way to go about saying, okay, it doesn't matter what that even integer is. I can always, or those two even integers are, I can always guarantee you that that result is still going to be even by using my definition. So I start with my hypothesis, what I'm getting, the if part. And I say, okay, given that piece of information, I want to show then that their sum, or a plus b, is also what? It's even. Well, what does it mean to be even? Gotta be multiple of 2. So all we have to do is just kind of write all of that out and use these definitions in a little bit of algebra. So whenever we do a proof, we always want to be very meticulous. We want to tell the reader what I get to assume. What am I getting? That's always coming from my hypothesis, that if statement. And read it to me again. What do we get to start off with? A, B, or even integers. So when we start off this entire premise, this discussion, we're going to let A and B be what? Even integers. So let A and B be even integers. There's something to it, right? If they're even, well, I know particular information about it from my definition. What does that mean? Well, that means then there exists few integers, which we'll just say are going to be called n and m. They can really be anything, right? What I'm using to represent them, that is. Such that A is going to be equal to 2 times that first integer n, and B is going to be equal to 2 times the other integer, m. So if you cook a lot, this is essentially a reason loss. Putting everything out on the table, it's all nice organized, you know, all the pieces we have to work with. But to make my final dish, I still have to figure out how to combine them all together. Well, what's the end result that I'm looking for? What am I trying to show? A plus B is even. It's equal to 2 times some other integer. Well, you know, this one's going to be relatively straightforward proof, so we can kind of start off with the argument directly. But again, just like if you're in algebra, calculus, whatever, you can take some time, write a draft of your argument on the side, figure out how it's going to work out. So let's consider A plus B. Well, if I want to show that this is an even number, I need to be able to show that it is 2 times some integer. Well, is leaving it as A plus B going to be helpful in that regard? No, right? There's not much I can do with it, but I do know 2 pieces of information. I know how I can rewrite A, how I can rewrite B. And when I do those rewritings, in both those cases, what is the important factor that then appears? The 2, right? That multiplication by 2. Well, by definition, because A and B are even, I know I can rewrite A, that's 2 times n, and I can rewrite B, that's 2 times m. All right, I've now put all of my ingredients into the frying pan, but I still have to do some work. I need to be able to show that this is 2 times some integer. So what can I do to that expression 2n plus 2m to make that happen? I heard some good ideas, but I wasn't able to decipher all. Too much mumble. Let's go with 1. Well, what do we know about internet? It's the only thing we know. The integers, right? And can I do anything more with that definition? Not really, right? It's a good instinct, right? See where I can break things further down. But I'll give you a hint, we've probably broken this problem down as far as. That's your opportunity, right? My goal is just to say this is 2 times something. Well, let those have a common factor of 2. What can I pull out? The common factor of 2, which means that this expression gets rewritten. Yeah, 2 times n plus m. Now, innately, we know if you take 2 integers and add them together, still get what type of number? An integer, right? Which means when I'm looking at this final form, this is 2 times integer. So I've looked at a plus b, and I've shown that I can write this as 2 times an integer. What can I conclude? Yes, so then that means what about a plus b? So on Wednesday, we're going to pick up another proof, but we're not done with this yet. Right? So there's one more thing that we always like to do with proofs. You might have seen or heard this before, especially if you grew up with like a algebra teacher who was really old school. Right? Am I done? Is there anything else I want to discuss with that theorem?
But how you do it, but I mean, nothing will play.
Yeah, we need some type of end symbol, right? To say there's no more need to discuss. I've said everything I want to say, and everything should be included. Right? There's 2 ways to do it. The more top modern way, put a nice little black square at the end. That is your indication that the proof is completed. There's nothing more to discuss. Okay. Another option, though, going to be old school. And if you take the history of math class, I think Dr. Stoltz teaches it, you get to look at the older papers. You might see this a lot. UVI. What happens to know what that stands for? Anyone know what language it comes from, maybe? It's Latin. Definitely Latin. It stands for, and I don't even remember without my note, don't worry. Quad, correct, and demonstrable. And this translates to what has been demonstrated or what was to be demonstrated. But most modern mathematicians would use some formulation of that little black square. Easier, also better for printing. You didn't know, like a lot of your rationalization rules, like square roots and fractions, stuff like that, are all motivated by how it be printed more so than proper form. But that's a side note, 10:50. Okay, so we're going to start Wednesday with another proof. Just that if you add two odd numbers, they become what? They become even. We'll be able to see why that's always the case. Right? But, and just as you're backing up, I'm still gonna talk. The point of proofs that we're gonna have is you start with the hypothesis that you're given. You're gonna use that, all the tools, definitions that you have at your disposal to then come to that conclusion being true as well. Right? Doesn't matter the context we do it in, that's how proofs are always gonna be. So we'll do that, and we'll probably pick up set theory a little bit on it. But I'll see y'all then. All right, see you Wednesday.